Electricians of the past were not able to wire receptacles with wires that did not extend past the front of the box. Consider the materials and tools available to electricians in earlier eras. Wire insulation consisted of cloth or rubber, which deteriorated more quickly than modern PVC insulation. This required more frequent replacement and often resulted in brittle, short wires. Wiring methods also differed. Early wiring often used knob and tube wiring or BX cable, which presented challenges for device termination and box fill. Space inside electrical boxes was more limited. Older boxes were often smaller than modern boxes, making it difficult to work with longer wire lengths. Furthermore, wire connectors and splicing techniques were less sophisticated. Wire nuts, for instance, weren't as ubiquitous or reliable as they are today. Soldering and taping connections were common, leading to bulkier splices. Electrical codes have evolved significantly. Modern codes mandate specific wire lengths within boxes to facilitate safe connections and future maintenance. Older codes were less stringent, leading to variations in wiring practices. The physical demands of the work were also greater. The electricians had to use hand tools extensively, which required significant physical effort and time. This could influence the length of wires they left in boxes. Consider that diagnostic tools were less advanced. Troubleshooting electrical problems in old wiring systems was more challenging due to the lack of sophisticated testing equipment. This made it more difficult to identify and correct wiring issues without potentially shortening the wires. The expertise and training of electricians varied. Formal apprenticeship programs and standardized training were not as prevalent as they are today. This resulted in inconsistencies in wiring practices. The environment also played a role. Conditions like moisture, temperature fluctuations, and pest infestations accelerated the deterioration of wiring in boxes, leading to the need for repairs and wire shortening. It is essential to exercise caution when working with old electrical wiring. Old wiring systems may not meet current safety standards and could pose a fire or shock hazard. Always energize the circuit before working on any electrical wiring. Wear appropriate personal protective equipment, including insulated gloves and eye protection. Inspect the wiring for signs of damage such as cracking, fraying, or discoloration. If the wiring is damaged or deteriorated, it should be replaced by a qualified electrician. Use appropriate tools for working with old wiring. Avoid using excessive force, which could damage the insulation or conductors. Make sure all connections are secure and properly insulated. Consider that you must follow the National Electrical Code, or NEC, and local electrical codes when working on any electrical system. The NEC provides detailed requirements for safe wiring practices, including wire sizing, overcurrent protection, and grounding. Local codes may have additional requirements or restrictions. When replacing old wiring, use modern wiring methods and materials. This will improve the safety and reliability of the electrical system. Obtain the necessary permits and inspections. Electrical work typically requires permits and inspections to ensure that it meets code requirements. If you are not comfortable working with electrical wiring, hire a qualified electrician. Electrical work can be dangerous, and it is important to have it done by someone who is trained and experienced. Let's discuss some specific wiring practices from the past. Knob and tube wiring, common in homes built before the 1940s, used porcelain knobs and tubes to support and insulate conductors. The wires were run through hollow wall spaces, and connections were made in open splices wrapped with friction tape. This type of wiring lacks a grounding conductor and is prone to damage from rodents and moisture. BX cable, also known as armored cable, consists of conductors wrapped in a flexible metal sheath. While it provides some mechanical protection, it can be difficult to work with and may not have a reliable grounding path. Early non-metallic cable, known as Romex, used rubber insulation that deteriorated over time. The lack of a separate grounding conductor in some older Romex cables is a significant safety concern. The evolution of electrical boxes is also noteworthy. Early boxes were often made of metal and were smaller than modern boxes. They may not have had adequate space for wire splices and device connections. Grounding methods have also improved. Older systems may not have had a dedicated grounding conductor, relying instead on metal conduit or the neutral conductor for grounding. This can create a shock hazard if the grounding path is interrupted. Overcurrent protection has become more sophisticated. Early fuse panels used Edison base fuses, which were easily replaced with fuses of higher amperage, creating a fire hazard. Circuit breakers provide more reliable overcurrent protection and are less prone to tampering. Wire connectors have also evolved. Wire nuts provide a secure and insulated connection, replacing the need for soldering and taping. Push-in connectors offer a quick and easy alternative for certain applications. Consider the impact of appliance usage. Homes in the past had fewer electrical appliances and lower power demands. As appliance usage increased, older wiring systems became overloaded, leading to overheating and potential fires. Lighting technology has also changed. Incandescent lighting was the primary light source in the past. Modern LED lighting is more energy efficient and produces less heat, reducing the strain on electrical systems. Understanding the history of electrical wiring is essential for working safely and effectively in older buildings. By recognizing the challenges faced by electricians in the past and the limitations of older wiring systems, it is possible to make informed decisions about repairs, upgrades, and safety measures. The electrical trade continually evolves, reflecting advancements in technology, safety standards, and energy efficiency. A deep understanding of past practices enriches the present-day electrician's knowledge base. The National Electrical Code, or NEC, plays a pivotal role in governing electrical installations. It's a comprehensive set of standards designed to ensure the safety of people and property. The NEC is updated every 3 years to incorporate new technologies and address emerging safety concerns. One crucial aspect of the NEC is its emphasis on proper grounding. Grounding provides a low impedance path for fault current, helping to protect against electrical shock. The NEC specifies detailed requirements for grounding electrodes, grounding conductors, and equipment grounding. Another key area covered by the NEC is overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. The NEC specifies the appropriate size and type of overcurrent protection for different circuits and equipment. Wire sizing is also a critical consideration. The NEC provides tables that specify the ampacity, or current carrying capacity, of different wire sizes based on factors such as insulation type, temperature rating, and installation method. Using the correct wire size is essential to prevent overheating and potential fires. Box fill is another important requirement. The NEC limits the number of conductors, devices, and fittings that can be installed in an electrical box. Overfilling a box can lead to overheating and difficulty making safe connections. Wiring methods are also regulated by the NEC. The code specifies the types of wiring methods that are permitted for different applications, such as rigid metal conduit, electrical metallic tubing, and non-metallic cable. Each wiring method has its own set of installation requirements. The NEC also addresses the installation of electrical equipment, such as receptacles, switches, and lighting fixtures. The code specifies the minimum mounting heights, clearances, and other requirements to ensure safe operation. The NEC is a complex and comprehensive document, and it is essential for electricians to stay up to date on the latest changes. Continuing education courses and professional certifications can help electricians maintain their knowledge and skills. In addition to the NEC, local jurisdictions may have their own electrical codes and regulations. It is important to comply with both the NEC and local requirements. Working with electricity can be dangerous, and it is essential to follow all safety precautions. Always to energize circuits before working on them and use appropriate personal protective equipment. If you are not comfortable working with electricity, hire a qualified electrician. Electrical safety is a shared responsibility, and it is important for everyone to be aware of the potential hazards and how to prevent them. Electrical codes, like the NEC Section 300.4 address protection against physical damage. NEC Section 310.15 covers opacity, temperature limitations and adjustment factors. NEC Section 250.118 covers types of equipment grounding conductors. NEC Table 310.16 provides allowed opacities of insulated conductors. NEC Section 406.4 covers general installation requirements for receptacles. NEC Section 210.21 deals with overcurrent device ratings. NEC Section 314.16 deals with calculating box fill. Electrical systems in Alaska present unique challenges due to the extreme climate and remote locations. The harsh winters can cause significant stress on electrical equipment and wiring, leading to increased maintenance and repair needs. The NEC recognizes the impact of ambient temperature on conductor ampacity. High temperatures can reduce the ampacity of conductors, while extremely low temperatures can make insulation brittle and prone to cracking. The NEC provides adjustment factors for conductor ampacity based on ambient temperature. In Alaska, it is crucial to use wiring and equipment that are rated for extreme temperatures. This includes using cold weather-rated cables and connectors, as well as ensuring that electrical enclosures are properly sealed to prevent moisture intrusion. The remote locations of many communities in Alaska also pose logistical challenges. Transporting materials and equipment can be difficult and expensive, and access to qualified electricians may be limited. This can make it more challenging to maintain and repair electrical systems. The NEC addresses the use of alternative power sources such as generators and solar panels in remote locations. These systems must be installed and maintained in accordance with the NEC and local regulations. Grounding is particularly important in Alaska due to the prevalence of permafrost. Permafrost can affect the conductivity of the earth, making it more difficult to establish a reliable grounding path. The NEC specifies alternative grounding methods for areas with permafrost, such as using ground rods that are driven deep into the earth. Electrical safety is paramount in Alaska due to the potential for extreme weather events, such as ice storms and flooding. These events can damage electrical equipment and wiring, creating a risk of fire and shock. It is essential to have regular electrical inspections and maintenance to identify and correct any potential hazards. Residents of Alaska should also be aware of the dangers of carbon monoxide poisoning from generators and other fuel-burning appliances. Carbon monoxide detectors should be installed in all homes, and appliances should be properly vented to the outside. Working with electricity in Alaska requires specialized knowledge and skills. Electricians must be familiar with the NEC local regulations and the unique challenges of the Alaskan environment. Continuing education and professional certifications are essential for staying up to date on the latest technologies and safety practices. The Alaskan electrical industry is committed to providing safe and reliable electrical services to residents and businesses throughout the state. By working together, electricians, contractors, and regulators can ensure that electrical systems in Alaska are installed and maintained to the highest standards of safety and quality. Firstly, older electrical boxes were often smaller than modern boxes, leading to shorter wire lengths. Secondly, wiring methods like knob and tube or early Romex often resulted in less available wire. Thirdly, electricians may have prioritized speed and efficiency, using the minimum amount of wire necessary.